This is Euclid Book 10, proposition number 4. And here is your illustration. Okay. And this one says, given 3 commensurable magnitudes to find their greatest common measure, let A, B, and C be 3 given commensurable magnitudes. Thus it is required to find the greatest common measure of A, B, and C. Let the greatest common measure of the 2 magnitudes A and B be taken, and let it be D. This is by Euclid Book 10, proposition number 3. So now we're going to say that D is the greatest common measure. D is the greatest common measure of A and B. Okay. Then D either measures C or it does not measure it. First, we're going to say that D measures C. Okay, now we're going to say, since D measures both of these, we're going to say now that D measures this as well. Okay. Since then D measures C, well, it also measures A and B, therefore D is a common measure of A, B, and C. Okay. And it is manifest that it is also the greatest, for a greater magnitude than the magnitude D does not measure A and B. Okay? So what we're saying here is that there is no line bigger than D that's going to measure both A and B. Because if they did, they'd also measure D, and we know that's not going to happen, so. Next, let D not measure C. Now we're going to say that D doesn't measure C. Okay. I say first that C and D are commensurable. For since A, B, and C are commensurable, some magnitude will measure them. And this will of course measure A and B also. So that it will also measure the greatest common measure of A and B, namely D. And this is by Euclid Book 10, proposition number 3, porism. Okay. But it also measures C, so that the said magnitude will measure C and D. Therefore C and D are commensurable. Alright. Now at this point you're probably very, very, very confused. Alright. So we're going to have some line. We haven't said which line it's going to be yet, but we're going to have some line that is going to be able to measure all 3 of these. Okay? And we obviously know if it's going to measure all 3 of them, it's going to measure A and B. And if it measures A and B, this same line that's measuring all 3 and these 2 is also going to measure this one. And since it's going to measure all 3 of these lines, these 2 lines, and this one, it's also going to measure this one. That's what he was saying. So this new line we're going to come up with is going to be able to measure both D and C. Because C and D are commensurable. So, now let their greatest common measure be taken and let it be E. E is the greatest common measure of A, B, and C. And this is by Euclid Book 10, proposition number 3. Since then E measures D, remember, if it measures all 3 of these, it's going to measure these 2, it's also going to measure that. We've already established that. While D measures A and B, so if E measures D and D measures A and B, therefore E will also measure A and B. E will now measure these 2. But E measures C. E measures C. Therefore E will measure A, B, and C. So this line here measures all 3 of them. Therefore E is the common measure of A, B, and C. Okay. I say next that it is also the greatest. For if possible, let there be some magnitude F greater than E, and let it measure A, B, and C. Now we're going to say that F is longer than E, but it also measures all three of them. Now, since F measures A, B, and C, it will also measure A and B. And it will measure the greatest common measure of A and B, which is by Euclid Book 10, proposition number 3, porism. But the greatest common measure of A and B is D. Therefore, now we're going to say that F measures D. But it measures C also, so F measures C and D. So F measures C, F measures D. Therefore, F will also measure the greatest common measure of C and D. This is by Euclid Book 10, proposition number 3, porism. But that is E. Now we're going to say that F, even though it's longer than E, now somehow measures E. We know that won't work. That's like saying 3 measures 2. It doesn't work that way. Therefore, no magnitude greater than the magnitude E will measure A, B, and C. E is the greatest measure of all three of these. Therefore, E is the greatest common measure of A, B, and C if D does not measure C. Okay. If D doesn't measure C, E will be the greatest common measure of all three of these. And if it measured D, D is itself the greatest common measure. Okay? So if D measures C, D is the greatest common measure of all three. But if D doesn't measure C, then E is the greatest common measure of all three. Therefore, the greatest common measure of the three given commensurable magnitudes has been found. And now we have another porism. From this, it is manifest that if a magnitude measures 3 magnitudes, it will also measure the greatest common measure. So, if we have a line and it measures all 3 of these, it will also measure the greatest common measure of all 3 of these. Similarly, too, with more magnitudes, the greatest common measure can be found and the porism can be extended. So basically what he's saying is, if you have 4 lines, okay, let's say you have 4 lines and you find their greatest common measure, their greatest common measure will not only measure the 4 lines, but it'll also measure the greatest common measure. That's what he's saying. And it goes on and on and on and on. Alright, I will tell you more in a future video. Stay tuned.